we tested it earlier. Let's see. Yeah. So hello, everyone. First off, I want to thank the organizers for once again giving me the opportunity to come talk about some of the things that we have been working on. So today, I'm going to talk about a system that we open source that's called FFS, and it basically stands for Fault Finding System. And I usually give this presentation with Daniel, so that's me and that's Daniel. Daniel couldn't make it because of some unfortunate passport issues, but you guys will have to just hear it from me. So one thing that's interesting or important to sort of get before we actually start talking about the system is like, what's the type of network that we are trying to troubleshoot or complement the monitoring of with this system. And I have this very compressed sort of version of what's used in most service providers or large scale like cloud companies or environments such as Facebook, which is a typical closed network, right? And even here, if you see this, you basically have on the left side, you have a host. On the right side, you have another host. You have a classic top of the rack, and then you have an aggregation layer, which in this case is 4 devices. You have what could be a spine layer with 6 devices, and then you have another layer which could be, for example, in this type of diagram, another data center, right? Like if you have one building, like on the left is one building, on the right is another building, this is a layer that interconnects the two of them, right? And this is, again, very compressed, but this is already in this topology, you can see that there is many potential paths that traffic can take. So to address some of the gaps that we have seen with this, we essentially open source something similar to what we have in production with the hope that this is useful for people dealing with these issues. And this is where this system comes to life, right? And I'll give you an example coming back to that topology. So what are we trying to, do? Essentially find the needle in the cloth, right? And like I said, with this topology, the typical scenario, or like a potential scenario of this is like, whoever is on call, or whoever is responsible for providing support for this, or actually operating this type of network, might come to the office, or this can happen on Saturday at 3 a.m., and they're very happy, and some service owner or someone that owns those hosts comes to them and says, hey, like I have these 2 hosts, like we have a replication job, or like this is a front end and that's the back end if you want to simplify it. We have all of our like application level graphs are indicating sadness, right? It's the network because it's always a network, so it's the network, right? Go figure it out. And what most people will do in this scenario, including us, is like we have a very robust what we call passive monitoring system. And this is a monitoring system that's basically utilizing signals that we get from the devices in some way or another, from some form of telemetry or some counter or some information that we extract out of the devices and then we put inside our pipelines, and this provides signal of, network element is happy, like this layer is happy or is unhappy or there is something broken, right? And obviously, most of the time for the common use cases, automation sort of kicks in. So this scenario happens, and now you are in this situation where you go check your passive monitoring. Your passive monitoring looks clean, right, as it always does, or most of the time it does, because if it didn't look clean, automation would have taken care of it, at least on our environment. And service owner is still saying, hey, my application looks horrible, figure it out. So I'll give you an example, and this, like this sort of gap between passive and active can happen for many reasons. I have examples from mundane to super exotic. I'll provide now an example that it's relatively mundane. It's mundane, but it's sad. It's exactly like the icon here. So you have this scenario, which happened to us. And then we investigate. And with like normal, classic, old school network troubleshooting, we basically narrow down out of all these links and out of all the devices connecting these 2 hosts, the problem lied in that one, right? And when we go look at the device looks perfectly normal. So our pipelines are not lying. Like the device doesn't have anything that indicates that it has a failure. It looks normal when it's compared to the other folks. Life is great, yet when this device is taken out of service, the problem stops. When this device is put back into service, there is eternal sadness, right? So we say, great. We keep narrowing it down with old school troubleshooting. We narrow this to a group of ports, and then we start saying, okay, maybe this is like a bad ASIC. We narrow it down even more to like a single interface, and we stop saying this is a bad ASIC, because like it no longer sort of fits what should be happening. And then we start like looking at low-level like physical counters. And at that point, we're already like reading hexadecimal and all that fun stuff that everybody loves to do. And we are like, at one point, one person says, hey, like, look, like, this is actually, like, this interface is reporting, like, millions of, like, symbol errors or something of that kind, right? And we go like, well, this is, like, normal, like, layer 1 problems, right? Like, why is this not in the normal counters and, like, going through the entire pipeline? And we go look at the normal counters, and normal counters report 0. So Q vendor. We talk with the vendor, and the vendor goes, yeah, in this system, in this architecture, there is, like, this process that essentially controls those low-level counters getting bubbled up to like the normal counters that everybody knows and understands. And that process seems to have crashed in that box a month ago. And the behavior of the OS is like, well, if that process doesn't tell me anything, the counters are all 0. And we're like, great. This essentially like this was hours and hours and hours, and then weeks of like trying to like unravel the mystery. And this was a process that crashed, wasn't reporting CRC errors on an interface, and this made it completely invisible to like traditional passive monitoring. So if the device doesn't know that it's broken, it's really hard for it to tell you that, hey, I have a problem, right? And that's a mundane example. So when we said, okay, how can we sort of open source what we have? What were our requirements? Our requirements were essentially we wanted to have traffic that was similar to production, and what I mean by this is most of this typical troubleshooting tends to happen using ICMP or some version of ICMP. We wanted something where we would actually inject traffic that could resemble what we do in prod, and in the actual version that we open source, we're using UDP. Changing this to TCP is not particularly difficult. We have our own sort of like requirements with UDP, and we like UDP, so it's UDP, but again, this can be tweaked. As you saw from the graph, we wanted this to be ECMP ready. We wanted this to be able to operate in like very wide networks, because even in the graph that I showed before, you're talking about a 4, 6, 8 sort of depth, when in reality, like in production, depending on your environment and depending what you're trying to do and your level of oversubscription, those layers can be 4, 8, 16, 24, 40, 48, right? We wanted this to be independent of the devices, and I think the example I just told you about indicates why. And we wanted this to be precise enough for automation. When you have fleets as large as the ones that we have, even if this is like a relatively odd corner case, you see it quite often. So we wanted something that would be able to indicate to us, hey, like we think with a high degree of confidence that the problem is within these 2 devices or within this circuit or within this box. An automation could go and take it out of service, so then a human, very relaxed after they had their coffee, can go look at it and actually understand if this is like a trivial hardware issue or if this is something more involved, right? So what are the building blocks of the proof of concept system that we essentially have, right? There's, let's say, 3 big blocks, and the first block is, in order to do this, we need to understand the topology. And to understand topology, we need something to do some form of tracing. And because we are trying to not do or use ICMP as less as possible, because it's not super ECMP, like ICMP tends to have like polarization issues in like wide ECMP networks. We have a particular element which is actually open source, and I'm going to talk about it in a little while. And we need this because we need to understand the forward and the reverse path, right? And with this information, we can actually start doing traffic generation, so we exercise those paths. It's like, well, I discovered that the topology has all these potential ways of getting between A and B. How do I exercise them? And then the part where we spend most of our time, which was basically building sort of the glue to put all of this together, which is essentially having like what we call a master, which coordinates all the tests, receives the inputs, applies a formula, and eventually gives you, hey, what you want to know, which is where do we think the problem exists, right? And the architecture, like from a system perspective, like I said, we have three roles in this type of solution: a master role, a pinger, and a ponger. And we built all of this essentially with a philosophy of web services. The idea is, we're using solutions, and we're using like technology stacks that are relatively well known, well understood, well documented by people that operate in these type of environments, but people that like have used open source. So we're using Python, things like Flask, which is a framework to do web services, Celery for task queuing, and Postgre as a backend, right? And on the pingers and the pongers, where we have to do like the tracing and we have to do the actual like active probing, we are using is basically iperf and Dublin traceroute. And the reason why those particular projects is because they are quite mature, they are well understood by the community. Their community is quite active, and they actually reply. And in the case of, for example, Dublin traceroute, the person that has done the most contributions actually worked in the same office as me, so that was super handy, right? So what's the workflow of this system? The workflow of the system is like, after this solution is deployed in your environment with whatever you might use to do this, like for example, Chef or Puppet or anything of that nature, the idea is that the devices or the hosts that you have defined as pingers and pongers essentially register back to the master. And this gives the master a view of like, okay, these are all the people I have available, so this will be useful when I want to actually do a test, right? And this also, like, there's a keep alive mechanism to, like if the device is going to go down, the server is going to go down because it's getting rebooted. Like, obviously, we don't want to be pinging things that do not exist, right? So when we trigger a test, the component that's responsible for starting this entire adventure is the master. The master has all this information because with the keep alive and the people that register, again, it also contains the parameters of what we want to do in terms of like, what's the range of ports, like how many trace routes do I want to do, like what are the limits so you don't, overdo this. And, in a production environment, you will usually just have this running all the time. But again, it depends on the environment, and every network is different. In this case, what I'm going to show you at the end is like we basically trigger this on demand, right? So when this happens, the pingers essentially receive a target list, and then they synchronize with the pongers. The first thing that happens is like we need to understand the forward path, and we need to understand the reverse path. So we're doing like traces from the pinger to the ponger, and vice versa, because you're trying to take into account that the potential for the return traffic not taking the same path as the forward traffic, right? And then after that's done, we essentially trigger iperf, which the parameters are all customizable to whatever makes sense in your environment. And this essentially gets received by the pingers. The pingers will indicate this information or will send this information back to the master. And then the master will run the algorithm, will run the formula that's actually described in the GitHub repository, and will give you like, hey, these are the subnets or the hosts that I think have the issue. And hopefully you have found the issue, or you have at least a better place to start your investigation, right? So, like I said, this is on GitHub. That's the URL. This is relatively easy also to find with Google if you guys want to check it out. We get notified by every comment, everything that happens there. So, like, if you guys are trying it out and it doesn't work as expected, or you're having issues getting it up and running, if you comment on the GitHub repository, this will go directly to Daniel or myself, and we try to be as responsible as possible. So on the demo, I was going to do this live, but we have some VPN issues, or I have some VPN issues, and I will explain a little bit like what's the context. So I actually have a video that will walk through and do this, right? But basically, we have this topology, and this topology is even smaller than the one I presented before, because actually when we were developing this, we spent more time, or I spent more time, actually trying to get ECMP in virtualized environments working properly than actually like doing the core of this. We saw all sorts of weird behavior, and eventually like got to the point where I was like, okay, the idea of this is to actually like, do this, present something to the community versus like me trying to fix the, work with vendors on fixing their virtualized platforms. So this is all actually running on hardware, right? Like this is actually like, we have this in a lab that's behind a very bad VPN. So we essentially have 2 core devices, 5 spines, 3 leaves, and essentially 3 hosts, which are just Linux boxes, right? We are going to, in what I'm going to show you, we are going to inject loss between that link in core 1 and spine 3. And the way that we're doing this, which I'll also show you, is essentially we have like this very small script that what it's doing is that it's injecting an ACL and then removing it like 10 seconds later, and the ACL is just dropping packets, you know, like the classical ACL where somebody fat fingers something, well, that's what it's doing. It's just getting added and remove it over the test cycle, which of course causes some loss. So let's give it a look, and I will comment as we go. I have this in essentially in a video, right? And the first thing is that we, which actually was a request from the community because we presented this in October or November, somewhere around that. We, like, all of this, like I said, is via web services, so essentially they are just exchanging and reading data structures in JSON because it's very easy to parse and very easy to see. So we built a UI that shows like the entire picture of this, right? And the UI actually has a typo because that's not how you write network. But yeah. And this is like from the point of view of the master, it will show you the last time it ran. It shows you who's registered as a pinger and who's registered as a ponger, which in this case, and from the topology that I just showed, essentially 3 PCs. And then like we also have PC1 here, which I mean we could have all the pingers, but like again, this is for demonstration purposes, so we just had one of them. And it shows you when the test starts running, it will tell you in what phase of that workflow we are, who are the targets list, because this is PC1, the target list here is PC2 and PC3. And when I trigger this off, like you will see the progress going along. Which again, how long this takes depends on your configuration and your setup and the size of the network. With what the configuration we had there, this will take around 5 minutes. But again, this can be faster or slower depending on the degree of precision and the size of the network that you have, right? And essentially, like what happened there in the UI is this was triggered, and now we're looking at the logs, like sort of like low-level debug in the PC2. And the first step, as I mentioned before, is like we need to do the traces. So here is like, okay, the traces have started against my 2 targets, which are PC3 and PC1. You can see there the source port, like the range, and then how many traces we're going to do. And what we're trying to do is essentially exercise ECMP, right? And this will give us like, before we start doing like iPerf, we need to understand. And like we will calculate all of the unique paths. And this is the super ACL script, and I will come back to this in a second. And here we have, okay, so I have all these unique paths. I need to trigger iPerf, and iPerf will, try to, using the same parameters, will run tests, right? And this is, for example, how this looks from a JSON perspective. This is reduced, but here you can see like this is very easy to read, and like it's obviously very easy to parse as well. Like if like from the point of view of the pinger, this is my source port, destination port. This is the path that I'm going to exercise. This gives us enough information to know, okay, if I run iPerf with the same parameters, this is the path I should be taking, assuming the network topology is stable, right? Like if the network topology is not stable, then that's another kind of issues. But if the network topology is not stable, most likely passive monitoring catches this, right? Because like you will be getting a signal if you have some sort of like, if you use BGP and you have something like BGP, you have something like BMP, you should be seeing this, right? And this is the device, and this is the script that does the ACL, which, as you can see here, what we're doing is like we indicated for a particular interface, which is one of the interfaces connecting those 2 devices that I mentioned, hey, like inject and add and remove an ACL. And it does that in like a 10-second interval, right? As the iPerfs are going, which will generate loss, right? And this is what we're showing here, right? And like I said, this was actually real hardware due to the ECMP issues in virtualized environments, which if anyone has experience with virtualized ECMP, please let me know, because I really want to virtualize this and just have it on the laptop. I really hate our physical lab. And like, this is the information that's been taken from the master. This JSON is essentially the skeleton that we're using to build that UI. And it has all the same information. So, and like this is what we were using before with like normal CLIs. But here, for example, you can see what I was talking about before. It's like, hey, like pinger 1 at this point in time is running iPerf. We are on step 3. This is going to 70%. like we can debug this either using the UI, which again, is not necessarily like a production UI, but it's more for like demonstration purposes and for development. But it could be expanded quite easily because essentially the backend information is just JSON, so it's just a matter of like, how do you choose to represent that, right? And then when iPerf finishes, the information also gets converted back into a JSON structure that has all the bits that we need to send to the master and then run the formula. And the JSON, I will open it in just a second, has this information, right? As you can see, like this is actually finishing up, and it's telling you, hey, for like all this path, this is how long I ran the test, and like here's the example, right? Like, as you can see, this is the results that will get sent back to the master, and with like this particular ponger and this particular parameters and this particular path, I ran this test for this number of seconds, this is how many bytes I sent, this was the rate, and this is the loss that I saw on that path, right? Which in the configuration that we have, they're basically doing a full mesh. So like everyone is a pinger and everyone is a ponger, but this could be fine-tuned if you were actually like, doing a trial or trying to build this for production purposes. You could essentially like fine-tune it to whatever makes sense. And other paths, for example, like this path has a 44% loss, the other one had 16%, and while you have others that are essentially clean, right? And now now we go back to the UI, and like if you look at this from the UI, like this actually finished. Like at this point, like the master has received all the results, which you can also see around here. The master has actually run the formula, and down here to the left, it provides the results, which again you could also get via JSON. And it indicates, hey, the subnet where I think the problem is, out of all of the ones that I discovered, is the subnet 131, which should be the one that I have here. Yeah, and that's it. And this is sort of how the system looks, right? And yeah, that's it. Thank you very much.
Any question? Looks like no questions.
Thank you.
And so next up we've got Brendan Jones talking about AMP active measurement. Thank you.
Cool, thank you. As Dave said, my name is Brendan. I'm a research programmer at the Modern Network Research Group at the University of Waikato. One of the things that I do during the day is I look after the AMP software, help get it running, collect measurements and see what goes on. So that works, yep. So hopefully nobody wanted to see anything about accelerated mobile pages or anything like that. When I say AMP, I mean the Active Measurement Project. So just very briefly, a lot of us already know what active measurement is, but at its basic level, it means we're putting packets onto the network and seeing what happens. So if we send a ping, we're putting ICMP echo on, echo request, hopefully getting an ICMP echo reply. If we're doing a trace route, we're putting packets on the network, seeing who replies to us. We're doing throughput tests, we're sending iPerfs, running iPerfs, whatever. That's all active measurement. And so we can contrast that with passive measurement, where somebody else is putting packets on the network, and we're seeing what we see with those. So all our packets that we're sending for active measurement they're not related to any useful user traffic, they're just purely for measurement purposes. So usually this is end-to-end or endpoint characteristics, and so we want to know how quickly that other end responds to us, or we want to know how much data we can put through. If we're doing CDNs or anycast sort of stuff, maybe we want to know which actual data center or which machine replied to us. If we're doing maybe DNS, we want to know what results we got back, or what was actually on that web server that we queried, or something like that. So we're doing that sort of tests. But if we do too much of this, we can interfere with the other traffic. So we have to strike a balance there between frequency of testing and getting good results that way, but not being too frequent such that we drown out our own results, or we make it so other users have an impacted network performance there. So there's a trade-off there. And we get good data compared to passive. We get different data compared to passive, so you have to weigh those up. So AMP is a system for doing active measurement like that in a continuous and a distributed fashion. So when I say it's continuous, I mean it's always running. It's just there in the background, it's doing its job. You don't need to remember to turn it on when an event's happening, or if something's broken, you don't need to find the web page and remember how to run it since the last time you had an outage 6 months ago or something. So it's just always there. It's always collecting data for you, so then you can bring it up and have a look. You can see normal behavior from the last however long it's been running for, compare and contrast with what's going on now. When I say it's distributed, it means that we can run it on multiple nodes around the network. We can run it from lots of vantage points and then combine all those measurements to see what's going on at any one particular point. We can see multiple paths into sites. We can see which links are perhaps running hot. We can see where latency is being increased or whatever. So multiple vantage points gives us better information to try to track down any problems that are actually going on. So as well as running the tests, AMP is also a system that's got a data exploration portion to it. So we've got a website there, there's graphs that you can look at, you can explore through them all, you can combine them, you can look at dashboards, you can see stuff there. But as well as that, there's also an event detection portion, so hopefully that you don't have to look at all those graphs. As soon as you've got a number of nodes, they start testing to lots of places, you've got exponentially growing graphs, you don't have time to look at all of those data, you don't have time to look at those graphs. And so hopefully we can try to identify bits that stand out as interesting, and then we can direct our attention towards those. So the original AMP software started as a project to measure American high-performance networks. In the 90s, there were huge amounts of American money government money going into building high-performance centres and connecting universities to these, and they wanted to make sure that the networks were running well and they're getting their return on investment there. Funding ran out in the mid-2000s for that, and most of those probes were decommissioned, but we kept running with the software, we kept working on it, and we've since redeveloped it into something, or evolved it into something a little bit new. So we took a whole lot of lessons from that original development, so we've moved away from writing stuff ourselves, where we know there's better libraries that have better knowledge on how that works, but also since then new libraries have actually come about that do all these things that we've done by hand previously. So now rather than packing our messages ourselves and doing our own messaging system, we can use things like RabbitMQ and protocol buffers. Rather than using flat files to store data, we've got things like databases. We've put things in Postgres now. And then recently InfluxDB as well, as that's come around and become a little bit more stable, a little bit more useful. So we're picking up new things as we go, just trying to improve it and do less of the bits that we don't know ourselves, and using well-known libraries for that. Grafana is another one that's come along lately. We haven't started to use that yet, but something like that is probably ideal for our web interface as well. But that's all sort of new since the project started. We've also moved away from a threaded model. The old system was heavily threaded. It had a lot of shared state. It fell over a little bit with that. So now everything's run in processes. It's all nice and isolated. Each one's individual. They don't need to communicate with each other to perform their tests. They only need to communicate with the system under test and then where they report the results back. So as well, that original AMP mesh, well, AMP test was a mesh. They would all test to each other in a full mesh to get every single path measured. We've also added tests to other bits of infrastructure that are outside of our control. So we test to DNS servers, we test to web servers, we test to a few other sorts of things. But it's things that we don't necessarily control, so we can't necessarily do tests that are too clever. We have to pretend to be other protocols. We have to do a DNS query or whatever. We can't necessarily blast them with a whole lot of data and hope that they'll respond to us with whatever measurements we want. So we've got this deployed across New Zealand. We've got 15 or so probes at universities and many ISPs around the country. Many of you are here. Thank you very much for your continued support with those. And there's also a couple of ISPs who have internal deployments now, so they're measuring customer connections or they're measuring various parts of their core networks. And so we're trying to grow this, and it's still ticking along, it's still growing. It's really good to see people using it. So at the moment, AMP does a whole lot of normal tests. We have tests that you're quite familiar with. We do ICMP latency, we do TCP latency, we do DNS, UDP latency as well. We do trace routes, we do throughput tests, we do web page downloads. Just recently, we've added YouTube video streaming as well. So that's quite interesting there. We can test and see how much buffering we get, whether videos play properly. But as we've gone on in time, our tests have moved slightly away from becoming raw network measurements. It's really nice to have latency, it's really nice to have throughput. They're really good numbers, we can see what's going on. But sometimes weird things happen. You know, we can run our latency test in isolation once a minute or once every 10 seconds or however often we want to run it. But then when you've got your something else combined with a couple of DNS queries and then something fetching something which is causing something else to be fetched, you can get weird interactions, or you can get race conditions where the timing of something's competing against something else. And so as we're going on, we're trying to make our tests a little bit more representative of what the users are hopefully seeing. You know, the raw numbers are really good for us. You know, we can measure, make sure that it's performing to spec, but maybe that's not the behavior the user is seeing. So we're trying to use the same software as them, or at least very similar techniques. There was a VoIP test added a few years ago that sends nicely spaced UDP packets. It's not a very accurate VoIP test, but it's better than sending one UDP packet, and so hopefully that can move along to using actual VoIP protocols, using signaling, using SIP, using all sorts of things like that. The original HTTP test was a simple get, it fetched one page and it timed it. That's since been changed to use multiple pipelines, to use pipelining, parallel connections. So it's more like a regular web browser, but again, it's still an idealized version of a web browser. So hopefully that'll move towards Chrome in the future, so that it is what the user is seeing. You know, we can run a web browser, we can see what's happening, we can see what DNS queries they're performing and why things might be going slow. And that's how the YouTube test currently works. So that was the first test bed for playing with Chrome there, was the YouTube test is actually run within Chromium. It fetches the page, it does everything as it should. And yeah, so we're trying to get away from raw bits and bytes necessarily, raw milliseconds, which we want to keep, but we want to give the user something that they can actually relate to as well. So just touching on the YouTube test there, yeah, the idea was to use Chromium. Just give us the view of what the user would see where they'd run that test, where they fetch that video and see what happens. It needs to behave just like a regular user, so if Google gives us a location we have to fetch that video from, we should obey it. We're not hard coding in what we think is the nearest CDN, the nearest site, and we're not streaming it as fast as we can, like you might do if you're using a YouTube downloader. We're obeying application flow control. We're doing all the things that a user would see. And so we want to report interesting statistics from that. So how long did it take before we could start watching that video? Did we have to wait 10 seconds to see it? How often did it buffer during the playback? Did it change video size because we couldn't keep up with the stream that we wanted to watch in HD or something? So we're trying to get results for the users and see what they can tell, results based on what the user would see and see what they can tell us. So the way the YouTube test is implemented, there's a nice simple web page that is instrumented using the YouTube iframe API. You can connect to this page and it will then download the YouTube video and trigger functions for all the events that happen. So when the video starts playing, there's an event triggered, we can count the time it starts. When it starts buffering, we can count the time it starts. We can add all these up and then combine that into a nice little data structure at the end. So the second part is a standalone implementation, a instantiation of a Chrome browser, a headless Chrome browser, which has recently come out. And so we're running our own version of that, which then we tell to fetch this page. It downloads it and then takes the results from the JavaScript in the page back into the C++ program, which then feeds back into our test. So it is just a web browser fetching a web page and reporting some JavaScript results. We could have possibly just used something like Selenium or Chromium headless manager things, but we wanted to, this was a test bed for a better HTTP test as well. And so later on when the HTTP test moves into a Chromium-based test, we'll be able to fetch all the information that comes out of performance navigation timing, which makes those really nice waterfall diagrams, which you might have seen. We can pull all that information out as well and then report on DNS timeouts, DNS lookup times. We can look at TCP connection times and things there. But unfortunately to do that, we had to instrument Chromium to add on extra headers, which lets us look at other people's data. It's our data, but data from other sites. And so that involved being able to modify network protocols, network headers, and then had to be done within Chromium and can't be done as a standalone external tool talking to Chromium. One problem with working with Chromium is that it is very big and it's very unwieldy and it moves very quickly. While trying to build whatever version was current when I started downloading it, I ran into some issues. Patches were up straight away. Not all of them would work with my build system, so I had to try to pick and choose. That started becoming a little bit unwieldy, unhelpful very quickly. Libraries I had to link against or symbols that I was looking for were hidden in random object files to start with, as headless was brand new. These have been moving into proper shared libraries and becoming stable in their names as well. So there's just a lot moving, a lot going on there, and I found the correct solution was to settle on using what YouTube and Ubuntu are using. Base myself around the same versions as them, and then everything's quite consistent, and I can take advantage of using their build system, their known patches, and have everything working there. Other problems that cropped up, just for interest, while playing with the YouTube test. It turns out if you try to link in at runtime a couple of object files that use files with the same name, they use symbols with the same names with different implementations, odd things happen. libSSL and libboringSSL both have different ideas about what functions take what arguments, what some of these structures look like, and then they crash deep inside the thing at odd times. So that took a little bit of figuring out there. As well as that, Chromium likes to fork itself on startups so that it can amortize some of the cost of initialization, and so it can later on fork itself with a good known copy and know that it's not been updated underneath it. My program, which is pretending to be Chromium, essentially, or running Chromium inside it, gets forked and then doesn't know what's going on with the arguments that it's been given, expecting to be a Chromium process, and falls over. So in the end, the right solution there was to split the behavior across two programs so that the AMP one that understood reporting and understood how to run the test arguments would start as one, and then that would start another one, which was a nice entirely standalone instance of Chromium, which would report its data back to the first one. So as we can see here, that's an AMPlet client. That's a single machine running on a single instance of AMP running on a single machine. We've got... So the scheduler here is always running. This process understands when tests are run, what tests should be run, what test arguments they should have, and it's responsible for starting up new processes such as these to run the tests themselves. So the scheduler wakes up, says there's an ICMP test due to run now with these arguments to these destinations. Let's start one off, and then it performs all the tests in parallel to the different targets and reports its results back to the central server, so using RabbitMQ, using protocol buffers. Scheduler, multiple of these can be running all at the same time, though you'd ideally try not to have too many of them running such that they collide with each other and impact your results. You can see there's a control process as well. Not all tests can be run on their own. The ICMP test is good because many targets will respond to ICMP. TCP tests are good because many targets will respond with you send it a SYN, it'll send you a SYNAC. If I want to send a throughput test, I want to send 10 seconds worth of data as fast as I can to a web server, it's probably going to ignore me, it's not going to like that. And so we can perform tests to other AMP nodes in our own area. We can say, please start me up a server now so that we can perform a cooperative test. So we can perform a one-way test of UDP stream or whatever we have. We can perform a throughput test and get the results sent back to us. So that's what that is for. And so each one of those is one of these circles here. These are all little individual AMP clients testing off to popular CDNs, popular websites, DNS servers, whatever it's interested in looking at. And so they all report their data back to the central collector into a report queue, which then is split into a couple. Some of it's stored into a database, which you can then access through the website, and the rest of it goes, and then a duplicate copy is sent through the event detection queue that then tries to pull out interesting events, puts them on the website as well. And we can also manage schedules through the website to send to the monitors so that they know what to test and where they need to test to. With the event detection, lots of network measurements, time series data, which is a pretty well understood, well understood area of event detection. There's lots of techniques for this. Unfortunately, some of these work really quickly, but not necessarily very accurately, and others take a lot longer time, but they get a lot more accurate. Or they only work on very level data. They don't work on anything that's noisy, or vice versa. And so we've tried to take a whole bunch of these techniques. We combine them together. We run all of them. That data that comes in through the eventing queue then gets sent to the 10, the 15, the 20 detectors. And as they flag events, they get combined. We say 2 or 3 of these triggered. Maybe there is something going on here. If there's only one triggering, or it's a low quality detector, there's only 1 or 2 triggering, we throw those away, or we hold on to them rather until we get some more confirmation. And so we're trying to do the best there to avoid false positives while still picking up interesting things. And at the moment we do get a lot of data, a lot of events. looking at the graphs, there's something going on there, but there's still work to be done on making sure that the ones that do come through are actionable. There's something that you can do. You don't want to be paged about something that's a non-event. Maybe you can get an email and you can look at that in the morning. So here's a quick look at the interface. This is the matrix that you might see on the front page. It's very simple, sources down the left and targets across the top. Colors are based on the latency. That's an ICMP latency graph from sources to the targets. You can see we're all generally pretty good there. Green is good. Yellow is less so. Yellow is still from 25 to 50 milliseconds. So everyone who's green is under that. And reds and oranges are getting into hundreds and 200s milliseconds. So at a glance, you can see what's going on. You can quickly flick through different source groups, different target groups, and see what it looks like. If we click on the event dashboard, we can see a list of events. They're grouped to some degree by using the traceroute data to combine them on ASs. So we can see that these three events all went through the same path. They went through the same AS. Maybe there's something going on in that one AS, and we'll group them together so that you can look at them. If we click on it, it opens up. We can see the 3 events there. And if we click on one of those events, it will take us through to the graphs. And we can see that's a latency graph. It looks a little bit like a smoke ping. And you can see 5 events that happened there on that day where the latency looks like it jumped up. So if we look at that, it successfully flagged a bunch of events there and click through and we see those. These slides I took out and re-uploaded, I thought, so why don't we skip them? So I also made some more interesting graphs. These graphs I took out of the app system just to try to clean them up to make them look a bit nicer for the web, for the projector. And so we've got a little bit of data now, and this system has been going since 2014. We've collected data from all of our sites to many of our targets across this time. I combined a bunch of them here. So this is 1 point per year. It's the median point per year from all of our monitors to Akamai. And we can see that the internet is getting closer. In 2014, we're picking things up somewhere in probably the west coast of America, 150 milliseconds away. Very quickly, that's all come a lot closer. We're looking at sub 10 milliseconds for a lot of that now. So, you know, we're in the country. We're in New Zealand. We're picking it up nice and local. All very good. Here's a similar graph for Cloudflare. Looks like they started off mostly in Australia 4 or 5 years ago, and then quite quickly as well, they all moved their stuff to Auckland or New Zealand locations, and so we've got a much better latency to them as well. There's still 2 or 3 holdouts there, that whether they're still going to Australia or whether they're just maybe not quite so well connected, the monitors that they're testing from within New Zealand there. Looking at V6, this is to Cloudflare as well. It follows a similar path. There's a lot fewer of our monitors that actually do V6 at the moment, but those that do, they're picking it up just as close. They've got very similar performance, V4 and V6. Same again, Facebook. Maybe they haven't quite reached New Zealand with any of their servers, but they're still picking it up. We're still getting it in Australia. A couple of people took a couple of monitors, maybe took a year or 2 longer, whether that was pairing, whether that was something else getting sorted, but they're all now very close. We're picking it up generally sub 50 milliseconds. That's pretty good. And their V6 as well follows very much a similar path, so we're looking at very comparable V4 and V6 routes. In some cases we do see much worse V6 performance than V4. Generally it's not the other way around though. Here's another graph. This is Google. This is from all of our monitors to Google across IPv4 ICMP. And again, mostly they're all in Australia. Very briefly, we were in New Zealand. Nice sub 5, sub 10 millisecond ranges there. But generally we're in Australia when we picked that up. There's one probe which had a very unlucky year where they ended up 300 milliseconds away for Google for quite a large portion of that time. And that's probably down to magic with CDNs and magic with DNS and trying to figure out where the best location to pick something up is. And the V6 looks very similar as well. It's all being served out of the same place. It's very comparable V4 and V6 routes, which is great. Speaking of DNS, this is an interesting graph from TradeMe. We can see that every time we query their DNS servers to do a lookup, we get round robin between Auckland and Wellington. It's just you don't expect to see it standing out so much, but when you're looking through the graphs to find an interesting one, it does leap out of you. It's an odd wave. You wonder what's going on, but then a couple of queries later, you can see, hang on, they've got a very short TTL, and then they return alternating Auckland and Wellington sites. So that's interesting. It moves around a little bit. You never quite know where you're going to get. Except that this is a traceroute graph showing AS and ASs in the path. You can see that each colour is based on one AS, and we don't actually change which ASs we visit to get there. So we start within the university. I think that's our probe, is university probe. These are RFC 1918 addresses, the ones that don't resolve. Back to the university, and then it's like very consistent set of paths to get there, regardless of whether we're going through to the Auckland probe or to the Auckland site or to the Wellington site. This is an interesting one that I found just while looking through the data. It's one of our probes to one of the New Zealand name servers. You can see that latency for IPv6 just sort of increases. Normal behaviour is about a millisecond or sub-millisecond. V4 continues to do that, but V6 just sort of creeps up. We've had a chat to them, we've had a look through the data. It's all very, very unsure what's going on at the moment, except that it happens every couple of weeks. It only affects IPv6 and only affects DNS on port 53. So who knows what magic's going on there, but the machine's perfectly responsive. It doesn't slow down. Still responds to ICMP fine. Their own monitoring's fine. Somebody in that path perhaps is doing something odd. I don't know. If you've got any ideas, let me know. What's in that path? What's going on there? So hopefully it was a rough idea of what AMP is, what we can do, some of the graphs we can get out of that. There's a whole lot of tests going on, and we'd like to have more people involved. Many ISPs here have probes. If you want one, if you want to host a probe, get in touch. If you want to run your own deployment, even if you want to keep all your data private, look at that, see what's going on, please get in touch. I have time to help out. I can get people going, I can get people set up. Just get in touch. If you have any ideas for tests, if there's anything that would be particularly useful for you, let me know, I'll add it. It really is just have a chat to me, let me know what we can do for you. If you're interested, there's URLs there to the website, to the GitHub. There's an email address there if you want to fire me an email. But yeah, I want to hear from you. Let me know what extra things we can add to AMP that would be helpful to you, what you need to do to help you run it. Otherwise, any questions?
I guess we already talked to Richard and perhaps you as well at some point, and from the degrees we're interested to actually do, using AMP as well. And one of the things that I think a lot of people might be interested in is called TWAMP. Is a protocol which allows you to actually, measure the times and a lot of measure the actual round trip, and it will actually timestamp at the point and return it. It would be good if AMP can support it because it's widely used in mobile networks and things like that.
Yeah, we've had a look at TWAMP. One issue is that you need synchronized clocks at both ends generally to help you out, I think, don't you? And that you timestamp it as you send it, as you receive it, and then as it comes out, it comes back. So if your clocks aren't synchronized, then you don't get necessarily accurate measurements, but maybe you don't need such precision if NTP is good enough, or if you've got GPS on the mobile sites. It is something we'd like to add though, if we could. Yeah, there's one down there.
Hi. Have you considered adding BCP38 measurements to the AMP network?
TCP38?
BCP38. So spoofing.
BCP38, sorry. No. Basically, is the short answer to that. We don't do any measurements for that. Is Scamper Matthew's project? So there is another academic in the group who does do measurements with network hygiene and things to make sure that advertisements aren't leaking and stuff like that. Spoofer, that's what it's called, the Spoofer project. I think emails get sent to the NZNOG mailing list too about networks that aren't behaving properly. Yeah. Cool.
So we got to the last session of the day. Thank you, Brendan. So next up we've got Thomas, is it Weeble, talking about 400 gig, and he's from Flex Optic. Thank you.
Thank you very much. Hi, my name is Thomas Weible from Flex Optics, and I am the co-founder of the company, together with my partner Marcus. I'm more in the environment of the technology when it comes to pluggable transceivers, building optical networks, and troubleshoot especially optical networks. And this presentation today is about upcoming, or it's more an outlook, what will be this year and next year coming out on pluggables when it comes to speed of 400 gigabit. I gave that presentation on the RIPE meeting last year, and Aaron from 6Connect came later on to me and said, hey Thomas, you have to replace the title of your presentation because what you're talking about is basically from Cyclops to Triclops, and he's right. So this presentation has two sections. It's a theory part, which I will start at the beginning, and then later on there's some hands-on stuff as well, and there you will understand the Triclops and also the Cyclops. So as I said, theory. It's a little bit back in high school days where we got the information about how a signal could look like. And when we got a modulated signal, like this one here, we got the interesting behavior that we have a high event and a low event. And our signal itself goes through those states, and having those two events, we can represent basically one bit. Why do I tell that? That's important to understand when we get the transformation from 100 gigabit now to 400 gigabit. That's 4 times the speed compared to 100 gigabit. And this theory will explain a little bit how we can achieve that, getting from 100 gigabit to 400 gigabit. But before I start there is also a term called the eye diagram. And I try to explain it on the eye diagram pretty much how this happens. And when I talk to network engineers and I say, hey, do you know the term eye diagram? They say, yeah, I know it, but I don't know the innards, and that's what I want to show. In principle, the goal is to have an open and a clear eye. That's the target of an eye diagram, but how can we achieve that? So when we have a sequence of 3 bits basically in a row, so for example here 0, 1, 0, it's pretty straightforward. Now 2 to the power of 3 gives us 8 different states, which basically look like this here. So we got 0, 1, 0, or even 0, 0, 0, or 1, 1, 1. Now when we overlap all 8 states of each other, we get something which looks like down here. So we overlapped all states with each other, and a real measurement and a real optical eye measurement looks basically like this then here, so quite similar. But what really makes an eye diagram, it's not only the signal itself, it's also that shape in the middle. So here we see our signals with the 3 different states going through, up and down. And this shape in the middle is really important because we want to somehow give our receiver, because we transmit something and the signal traverses on the fiber, we want to give the receiver a chance to understand that signal itself. So, and the receiver needs somehow the capability to differentiate between high and low, because otherwise, when it's in the middle, it's basically garbage, and the receiver can't distinguish between a high and low. So what we really want to avoid is, we want to avoid dodgy eyes. This was me trying to play ice hockey. I wasn't very successful, but yeah. Now moving on with 400 gigabit, it looks a little bit different. So back to our theory page, you might remember that rectangle shape, but now what I did, I added 2 intermediate steps in our signal. So instead of having just low and the high event, we got now low, H1, H2, and H3. And that's pretty helpful. So we can do this with modulation, basically. So we got 4 different events, and 2 to the power of 2 gives 4. So we can represent now 2 bits in one signal. And how does this eye diagram looks then? It's more like a monster with 3 eyes. So that's the eye diagram of a PAM4. This is the 4-level pulse amplitude modulation scheme. That's how it looks like. So we got our 4 different events here and going through those states. And the great thing is now as I said, we can represent now 2 bits, which we see over there, but we kept the frequency. That's a really important thing. So looking at the first eye diagram we saw with the on-off keying, we had the same frequency like this one now, but we just doubled the amount of data rate because we used a modulation scheme, the PAM4 modulation, within the same frequency. So, and that's one key component for 400 gigabit. It's still not quadruple, it's double the data rate now, just because of the modulation, but coming to the next step from 2 to 4, I will show in the hands-on one. Before I do that, I do a recap on 100 gigabit transceivers when you open them up. So when you open up a 400 gigabit transceiver, you pretty much see 2 sections. First of all, you got an electrical side on the left side. You got an electrical connector connecting to your host, to your switch, your router. And what is so special about this electrical side? We have 4 lanes running 25 gigabit basically. So these 4 lanes are connected to an optical engine, also running at a speed of 25 gigabit 4 times. Now, for 400 gigabit, it looks a little bit different. For the electrical side will increase the amount of lanes from 4 to 8. And as I introduced previously, the PAM4 modulation, where we kept the frequency, but we double the amount of data from 25 gigabit to 50 gigabit, we get now 8 lanes running at 50 gigabit, and when you do the math, you get 400 gigabit. These 8 lanes are connected to a optical engine running also 8 optical TEECs, transmitters, and 8 receivers running at a speed with 50 gigabit. That will be the first generation, and when there will be a first generation, there also will be a second generation, which looks like this. The electrical side won't change much, beside the fact there will be placed a gearbox on it. So what is this gearbox doing? This gearbox is taking those 8 electrical lanes and combines them to 4 lanes. Just basically what it does, it increases the speed or the frequency. So we are running here now 4 times 100 gigabit, driving an optical engine with 4 transmitters and 4 receivers. So why do we make it so complicated and say, hey, we're going to place here a gearbox that's an additional component, a chip, it's an ASIC. This is going to be expensive. Yes, it is. It's a little bit more complicated to place a chip there. And also, you have to add components, and this drives costs high. But if you would run the electrical side with 4 times 100 gigabit, this would even drive the costs even much higher, because you would need to have to increase the frequency. And when you look at today's PCB substrates, they are not capable to handle that frequencies. There are substrates out there which can handle it, but they are freaking expensive the longer the traces are, and you don't want to pay for that. So it's even cheaper just to place a chip on it, which makes a really short connection over with the 4 times 100 gigabit to the optical engine. And that's one of the root causes, having that gearbox in there. So when we put that all together into a nice form factor, you might be familiar with the QSFP28, which we see on the top. That's the current state-of-the-art 100 gigabit transceiver. Now there will be, for 400 gigabit, there will be 2 new types coming out on the market this year. It's first of all the QSFP-DD, which is pretty much from the shape like a QSFP28, and the size and dimensions. And the nice thing about a QSFP-DD is it's more the port. So a QSFP-DD port can handle a QSFP28, so it's backwards compatible. So when you have a QSFP-DD port running at 400 gigabit, you're also able to run a 100 gigabit QSFP28 in that same port. Sadly, not the other way around, but and that's pretty helpful. Now, how is that made? It's pretty simple physics. A QSFP-DD slot has 2 connector rows. So when you plug in a QSFP-DD in a QSFP-DD slot, both connector rows are connected. Now, when you plug in a QSFP28 in a QSFP-DD slot, only the first row will connect here, and the second one isn't used at all. And that's how it's made. Pretty simple physics here. The second type of 400 gigabit will be the OSFP. It's a little bit bigger compared to a QSFP-DD, but it has some interesting, an interesting behavior. It has an integrated heatsink inside in the housing. Why is that needed? We'll see later on when it comes to the power consumption. From the physics as well, I mentioned that size of 35 millimeter, the portion which sticks out of your first unit of your switch, for example. And why do I mention that? When back in the days, 6, 7 years ago, when the first 10 gig DWDM SFP pluses were launched, there was this huge heatsink in front of where you plug in your LC duplex receptacle. And we got calls from customers saying, hey, that's great that we got now 10 gig DWDM SFP pluses, but we can't close our rack doors any longer because it's way too long. Why do I mention it? It won't change because from the industry agreed, we are able, the maximum size which can stick out of of the transceiver is 35 millimeters. And bear that in mind because you need space in front of from the first rack unit to your door of your rack, basically, roughly 150 millimeters. So you have those 35 millimeters from the transceiver. You get an LC plug with roughly 50 millimeters, and then the fiber should itself get also a little bit bent radius because when you squeeze it too hard, your signal won't go through. And combining this with the fact that latest switch generations, when you look at top of the rack switches, 1U pizza boxes, they get really deep. And so we have seen customers that they got really issues deploying their gear within 1,000 millimeter depth rack, so they better go for 1,200 millimeters. What else? So what can we connect on the optical side of those 400 gigabit transceivers? For sure, we can back-to-back connect them from 400 gigabit to 400 gigabit, but there will be some new applications as well. And one I want to show now here, it's mainly a breakout scenario where you break out the 400 gigabit from your QSFP-DD or OSFP. It doesn't matter. You can break it out to 4 times 100 gigabit, and these are really one lambda carrying 100 gigabit, and you can connect it to a QSFP28. Not the ones which we have currently deployed because they don't support the 100 gigabit on a single lambda, they do it on 4 lambdas. There will be a new generation of QSFP28 coming out as well, having a single lambda, 100 gigabit. And with the time, we also got a micro QSFP or SFP-DD. But the main drivers of those single lambda 100 gigabit transceivers is QSFP-DD and OSFP because this technology is built for them. 4 times 100 gigabit, and then take 1 time 100 gigabit built in a different form factor. Yeah. Now, when it comes to IEEE and standardization, I also would like to do a recap to 100 gigabit, which is pretty simple. We're looking at single mode. The IEEE, back in the days, they just defined LR4 as a standard. Which is 10 kilometers, and spacing of our wavelength is 5 nanometer. It's the LAN WDM. That's it. Technology-wise, other solutions are possible on single mode, like CWDM4 or CLR4, or even the parallel single mode breakout solutions, which you see up here, or 20 nanometer spacing. But the problem was the IEEE never defined them as a standard. And the problem is when you don't have a standard, you can't interconnect with someone else because when you're talking the wrong language, it doesn't work at all. That's something which was definitely learned when IEEE defined 400 gigabit as a standard. They introduced now the DR4 as a standard, which is mainly used for the breakout mode up to 500 meters, a parallel single mode. So you can do, this breakout 4 times 100 gigabit scenario. And a new one, the FR4, which is the CWDM 20 nanometer spacing, and that's quite interesting. So why is that CWDM 20 nanometer spacing so interesting? It is cheaper to build than the LAN WDM 5 nanometer. because stabilizing a laser with a spacing of 20 nanometer is less expensive comparing with 5 nanometer of a laser to keep it stable over the lifetime of that transceiver. Yeah, it will be available up to 2 kilometers, and LR4 for sure up to 10 kilometers. When I introduced at the beginning the OSFP, I mentioned something about a heatsink, and the heatsink is an important thing to get rid of the heat. Now, first of all, we have to pump in a lot of power in such a transceiver, then he makes some magic, and we generate basically heat. Comparing the 400 gigabit transceivers with the 100 gigabit ones, there's a major difference in heat dissipation and power consumption. So the 100 gigabit ones, like QSFP28, were able to carry a load of 4 to 5 watts and also capable to get rid of that heat, which was generated. Now QSFP-DD and OSFP will be able and capable to handle up to 12 or even the OSFP up to 15 watts. Now, why is that so important to put in such a lot of power is to drive that technology that we are able to how to say, not only can do distances up to 10 kilometers, which we're currently doing with 100 gigabit, we want to go beyond that. And going beyond 10 kilometers, like applications like 25 kilometers or 80 kilometers coherent DWDM, that's something which consumes a lot of power. And that was one target when defining these pluggable modules, that they are able to handle up to 15 watts, that we can place a DSP inside and provide coherent solutions, which were never be able to do on the 100 gigabit QSFP28, for example. On another thing which is important to know, when you have 15 watts just on the optical side, and you imagine you have a switch with 32 ports, carrying 32 ports of OSFP, and each port is doing 15 watts, this is only just for the optical side 500 watts of power consumption and heat dissipation, and not taking in consideration that there is memory, CPU, and all the other stuff which makes a switch a switch. So you might end up with a power consumption of up to 1 kilowatt for a 1U switch, which is quite a lot. Right. Now, where will that future go? Or for 400 gigabit, as I said, the lesson we learned from 100 gigabit, and it will definitely be a target for both form factors, basically, getting there to do coherent DWDM inside or with such a pluggable with the proper components doing the DSP, for example. When you ask me at the current stage, looking at the market, I haven't. Well, there are some announcements that there will be switches available if it's either QSFP or OSFP. OSFP is mainly driven by Arista in these days, and there was an announcement last year and at the end of last year that they will gonna publish a 7060 X4 platform, and it will be available somehow next month, this platform. So they will be somehow, what I see on the market, the first one who bring out a 400 gigabit switch. But they will also support, beside the OSFP, they're also gonna will support the QSFP-DD. Yeah, that's it from my side. If there are questions, let me know. Thank you very much.
Question in the room?
Okay.
Oh, look.
I'll try and put this question simply. So with you've got say 4 or 8 lanes coming out of your SFP. That's great if you've got 4 or 8 fibers, right, to pop them into.
When you look at, I can go back. Quite slow. Yes and no, it depends on the application. When you do multi-mode, you will have 8 fibers 4 TX, 4 RX, but when it comes to single mode, there will be a multiplexer, demultiplexer inside. So you have 40 foot wavelength, which you multiplex together on a single fiber then.
Because that was kind of my question. It'd be nice to have 4 different wavelengths coming out, so you can just whack them into a CWDM system.
Okay. All right. So, thank you very much.
Okay, thank you to all the speakers. So that's the end of day 1 of NZNOG. We're actually finishing 20 minutes early, so nice early kind of finish. So the venue here closes at 5:30 this evening. So buses will be collecting people from outside the venue at 6 o'clock this evening. So we've got, I think, 3 buses taking us out to Napier Sailing Club. So buses will then return you back to this venue at, leave the sailing club at 10 o'clock, 10:30 and 11 o'clock tonight. And then we're starting off again tomorrow at 9 AM in the morning. So I think the venue opens about 8 o'clock in the morning. So we'll see you tonight for the dinner and then again tomorrow. Thank you.